Hi, I am Tom Monnier and I'm going to present our work on deep transformation-invariant clustering. In a nutshell, we introduced a deep clustering framework that jointly learns prototypes and prototype-to-sample alignment to match raw input data. It is state-of-the-art, strongly interpretable, and can be applied to web image collections. Why do traditional clustering algorithms fail on images? If you look at standard clustering algorithms, they typically rely on distances, which are not invariant to image transformations. Even in the simplest case of translated images, resulting L2 distance is not informative if images are not aligned. And this observation holds for more complex image transformations, like order spatial modification, morphological deformations, or color changes. For this reason, most image clustering methods perform clustering in a feature space that is likely to resolve invariance. Learning meaningful representations is challenging, and this type of methods yields the best results on standard benchmarks. However, they still struggle with real images, and clustering results are difficult to interpret. On the contrary, a second set of approaches aims at explicitly modeling transformations to align images in pixel space before clustering them. Although much more interpretable, they typically involve complex optimizations, limiting their application to simple alignments and small datasets. We propose to revisit this line of works and to explicitly resolve transformation invariants with deep learning. In this work, we present a prototype-based approach that performs clustering in pixel space by explicitly aligning prototypes using deep learning. By modeling complex alignments, we demonstrate state-of-the-art results on standard benchmarks, as well as applicability to unfiltered web image collections like Instagram hashtags. Prototype-based clustering methods typically aim at learning a set of prototypes by minimizing a quantization error. Once the problem is solved, each sample is then assigned to the closest prototype. Our key insight is to explicitly model transformations, in this case a rotation, to which we want to make the clustering invariant. For each sample, we first predict alignments of the prototypes, then use the transformed prototypes to compute the quantization error. We propose to predict alignments using deep learning and to jointly learn prototype and deep alignment by minimizing a single quantization loss. More formally, gradient-based prototype methods optimize a set of prototypes to minimize a loss, which evaluates how well they represent the samples. For example, in k-means, L corresponds to the L2 distance to the closest prototype. Assuming we have access to a group of transformations, T, parameterized by beta, one can instead minimize the following transformation invariant loss, where the minimum over betas is taken for each sample independently. We provide proof of the loss invariance to prototypes transformations in our paper. We experimentally show it is faster and actually better to instead learn k-deep prototype-specific predictors, where each predictor aims at associating to each sample the transformation parameters minimizing the loss. Because parameter predictors are now shared for all the samples, this structure naturally regularizes the parameters for each sample, leading to better clustering results, especially when modeling complex transformations. We apply this framework to classical gradient-based adaptations of k-means and Gaussian mixture model. For k-means, the quantization loss to minimize is the average Euclidean distance between each sample and the closest prototype. This loss can be adapted to a deep transformation invariant loss, which we simply minimize jointly over prototypes and deep parameter predictors using a batch gradient descent algorithms. For Gaussian mixture model, the loss to minimize is the negative log likelihood, where μk and sigma k are the mean and covariance matrices, and pk are the mixing probabilities. Similarly, it can be adapted to a deep transformation invariant loss, which is minimized over Gaussian parameters, mixing probabilities, and deep predictors using a gradient-based expectation maximization procedure. Learning image transformations is a hard task, and we propose to model transformations as a sequence of transformation modules which are successively applied to the prototypes. A transformation module can take the form of any parametric transformation that is differentiable. We define three useful types of modules, namely the spatial transformers from Jaderberg et al., a color transformation corresponding to a channel-wise affine transformation, and finally a morphological transformation that predicts dilation and erosion. We found two intuitive elements were key to obtain good results. We adopted a curriculum learning strategy to learn the transformations sequentially starting by the simplest ones, and we reassign clusters that become empty during training, which is rather standard for a quantization method. How does it look like on real image cases? Here is an MNIST query sample with a given learned prototype. For our MNIST dataset, we first learn to coarsely align the prototype to the sample using a single affine transformation. Then we learn to adapt the thickness of the prototype using our morphological transformation. Finally, we model local elastic deformations using a thin plate spline transformation. Note, our resulting prototype matches accurately the query sample. We evaluated our approach on standard image clustering benchmarks. We visually separated feature-based methods and pixel-based ones and marked methods that use data augmentation or ad hoc data representation. Both DTI K-means and DTI GMM obtain results on par with the best concurrent methods. In particular, we improved state-of-the-art on both Fashion MNIST and HVHN datasets by a significant margin. Compared to most concurrent methods, we believe our approach also has the advantage to be strongly interpretable. When we apply standard K-means, we observe that learned prototypes are mainly driven by color spatial biases. By explicitly modeling color and spatial alignments, our method yields much better and much sharper prototypes. The sharpness of our prototypes, here at the top in purple, directly stems from the quality of the learned transformations. For a given query sample, in blue, we show aligned prototypes and highlight the closest prototype in green. Note how we manage to accurately model complex transformations like thickness or local elastic deformations. Similarly, when applied to object datasets like Fashion MNIST, we manage to accurately deform the prototypes to match the different object instances. For colored images, like these colored MNIST datasets, we explicitly resolve color invariance with the dedicated module. In contrast to concurrent methods, it enables us to directly work with colored images without any preprocessing or manual ad hoc representations like Sobel filters. We also demonstrate our approach robustness by visualizing clustering results on web photo collections like this collection of Florence images. We show the 4 best qualitative prototypes learned with our approach when applied with 20 clusters. They are extremely sharp and detailed. Except few outlier samples, the clusters found have a surprisingly high purity. Even for such complex images, we managed to model real transformations like illumination variations and viewpoint changes. When we compare the full set of prototypes learned with standard K-mean and our deep transformation-invariant adaptations, the results are impressive. The simple combination of our color and spatial alignments allows us to turn a failing K-means algorithm into a successful clustering method that is able to discover meaningful clusters. Finally, we show that our clustering method could be applied to unfiltered sets of Instagram images associated to specific hashtags. Even if most images look like noise, we managed to discover iconic photos and iconic poses. In particular, we recognize a Santa in a red chair, alone or seated next to 2 children. These successful results are validated on other Instagram hashtags like Bali Temple, Trevi Fountain, or Wedding Kiss. To the best of our knowledge, we are the first to report this type of results from raw social network image collections. Interestingly, some of the prototypes are still really sharp, like the top left one. By looking at associating samples, we found that it actually corresponds to an iconic photograph usually shot when traveling to Bali. To conclude, we introduced a deep clustering approach, which jointly learns prototypes and transformation-invariant assignments to match raw input data. Despite its apparent simplicity, our method comes with several advantages, including state-of-the-art performances and a strong interpretability of clustering results. Finally, note that the framework is generic and could be applied to other types of data with known transformation-invariant semantics like 3D point clouds or time series. The code is online. Check out our paper for additional experiments and details. Thanks.